Said I came out of retirement to give you guys a talk. I actually had to modify my nap schedule so I could be here today. Thomas, great to see you. The Gates. Today's talk is going to be an introduction to DC converters. And I'm going to start with an introduction, then talk about AC to AC converters versus DC to DC converters. Then talk about LDOs, buck converters, boost converters, and at the end of the talk, if there's still a little time, I have a special bonus talk. It's really about, I should have included it with the integrated circuit reliability lecture, but I ran out of time, so it's on reliability. I have a story about how I got picked for this talk today, and I'm in retirement now and living on a fixed income. So, DC converters are part of a larger family of products called PMICs, and that stands for Power Management ICs. And PMICs are used to control the flow of power to a wide variety of systems, like cell phones, automobiles, spacecraft. Now, the job of the DC to DC converter is to convert an input voltage to a desired output voltage that can then be used as a power source for other circuitry. Before I discuss DC to DC converters, I'd like to take a few minutes to review AC to AC converters, which we're all kind of familiar with. It's what we call transformers. Anytime you run a current through a wire, it creates a magnetic field. In grade school, you may have done a science project where you created an electromagnet by coiling a wire around a nail and then hooking it up to a battery like I show here. Now, this simple experiment demonstrates how electrical current generates magnetic fields. In addition, it shows how you can concentrate a magnetic field by putting a coil of wire and making all those field lines overlap each other, like in the drawing on the right-hand side here. So transformers take advantage of this principle by placing two coils right on top of each other, such that they couple through a process known as electromagnetic induction. Electromagnetic induction requires a constant changing magnetic field. Therefore, transformers only work with AC signals. So an ideal transformer is lossless, which means 100% of the input power gets converted to the output power. Now, in reality, transformers aren't that good, but they're still pretty good. They're like 97 to 99% efficient, which isn't too bad. And what that means is the input power, voltage in times current in, is pretty much equal to the output power, which is voltage out times current out. This should probably be a review for all of you. The drawing shown in the lower right here is a step-down transformer. Its job is to take a high voltage, low current input and convert it to a low voltage, high current output. And for AC converters, it does this by having a greater number of turns in the primary coil, which is the input coil, or windings, than the secondary coil. So the output voltage will be proportional to this turns ratio. In this case, we see a lot more turns on the primary coil on the left there. We have step-down transformers like this used all over the place in the US. And they're very common sitting on the pole outside your house. They step down the roughly 7,000 volts on the pole to about 120 volts coming into your house. And that would be about a 60-to-1 turns ratio. What if you want, instead of stepping down the voltage, what if you want to step up the voltage? Well, it's done exactly the same way, at least for AC to AC converters. And here we show a step-up transformer on the right, the lower corner here. To increase the output voltage, all you have to do is place more turns in the secondary winding than the primary winding. And once again, the output voltage will be proportional to the turns ratio. Now, for very long distance power transmission, we're talking a couple hundred miles. It's common to use voltages as high as 500 kilovolts, very, very high voltages. And those high voltages are used so that the current that they're transmitting can be very small. We want to keep those currents small because currents cause resistive heating in your power lines or losses. Okay, so why am I going to all this trouble to talk about AC to AC converters when I really wanted to talk about DC to DC converters? So here's the connection. So what we've seen, it's fairly easy to either step up or step down AC voltages. Well, what if you want to do that same thing with a DC voltage? Well, that's the job of a DC to DC converter. However, things get a little and maybe a lot more complicated when you have to do it with DC voltage. It's really easy with AC, but DC, not so much. So there are a bunch of different types of DC converters. I'm going to talk about a couple of them. There's probably a half dozen I didn't make my list here. I did discuss charge pumps in an earlier lecture a few months ago. And charge pumps might be considered a step-up converter. You're trying to increase an input voltage by stepping it up with a charge pump. Today, I'll talk about two step-down converters and another step-up converter. I'm going to talk about LDOs, that's a step-down converter, buck converters, and boost converters. Okay, so what is an LDO? The purpose of an LDO, as I said, is to step down a DC voltage. Let's say you have a 5-volt input voltage, but you really need 3 volts out. An LDO can take that 5-volt in and generate the 3-volt output that you need. Now, it does this by inserting a series element. I'm kind of showing that in red up here. That drops the voltage needed to make the output go to wherever you want it to go. So in this case, we want that series element to drop 2 volts such that our 5-volt input is converted to a 3-volt output. Now, in this simple case, a resistor divider might work. However, things get a lot more complicated once you start varying the input voltage and the load resistor, and you'll see as we move along, you get a little more complicated. So let's say we want to maintain that same 3-volt output over a wide range of input voltages and load resistors. So we want to vary the input voltage all over the place. We want to pull different amounts of load current out, but we want our output to sit right smack at 3 volts all the time. So another way to say this is we want to generate a regulated output voltage that's fairly independent of the input voltage, of the load, and of temperature. So to do this, we're going to need some type of stable reference voltage and a feedback loop to set and maintain our output voltage. And what I show here is a very simple example of how that may be accomplished. And what I'm going to do is I'm going to walk through each part of this network and try to explain how it works. The first thing I want to talk about is we call the pass device. And the series element in this schematic is a PMOS transistor, and that's shown in red down here. And just like before, it creates a voltage drop between V in and V out that brings down the V in voltage down to whatever output voltage we desire. In this case, we want 2 volts to drop across the PMOS device. Due to the feedback loop, this circuit can adjust that drop across the pass device to maintain the 3-volt output, even if V in changes or the load changes. And like I said, the PMOS device is referred to as the pass device. You'll hear designers talk about pass devices all the time. It really just means the big freaking output transistor. So, in LDOs, the output voltage is regulated by the pass device dropping voltage and dissipating power. So we're going to get to that power dissipation in a few slides. But basically, you're dropping voltage and dissipating power in the pass device. Next part I want to talk about is the air ramp. And I show that in red here. And the air ramp, its job is to compare the reference voltage and the sensed output voltage, and then drive the pass device to whatever it needs to get the loop to regulate. And the gain of the air ramp increases the accuracy of the regulated output voltage. However, as we all know, when you get gain, you have the potential for oscillation. So stability is always a concern when you have gain. And I'll talk about that briefly in another slide here. but just want to mention, you have to take a lot of care. You have to make sure that you compensate the loop to maintain stability under all operating conditions, the input voltage, the output load, and temperature. Next, I wanted to talk about the reference voltage shown in red down on the left here. VREF provides a stable reference voltage that's used to set the output. VREF can be generated internally using a bandgap reference. I think a few months ago, I talked about how to generate a bandgap reference or how we might make a bandgap reference on chip. Or you can bring a reference voltage in from an outside source if you want to. VREF generally sets the low end of the voltage range that the LDO is going to be able to regulate at. Therefore, you typically set it only at a couple hundred millivolts. So this example here, I'm setting it at 500 millivolts, half a volt. Once again, VREF, since this is your reference voltage, it has to be stable under all operating conditions, input voltage, output voltage, load current, temperature. So a bandgap's usually a pretty good circuit to use in this location. Sense resistors. So these sense resistors are shown on the right side of the drawing here, and they set the closed loop gain of this system. Now the ratio of the sense resistors is used to gain up the reference voltage to produce the desired regulated output voltage. The sense resistors, they can be internal inside the LDO if the LDO is designed to produce a fixed output voltage. I think there are LDOs on the market that do that. Or you can have the sense resistors be external, allowing the user to set the output voltage by picking a ratio of resistors here. So in this case, the sense resistors are configured to gain up the voltage by a factor of 6. So basically, we're taking our half-volt reference here, we're gaining it up by a factor of 6, and that gives us our 3-volt output. The dropout. The term dropout refers to the difference in voltage between the input and the output. And the name LDO stands for low dropout. Now, typically an LDO will have a range of output voltages it can produce. And that means the LDO is capable of accurately regulating the output voltage up to within a few hundred millivolts of VN. So very close to VN. And what I'm showing in the example here, we're only 300 millivolts away from the input voltage. So we're getting pretty close. Now you can see that achieving low dropout, especially when you're trying to pull a lot of current out of this device, it can get kind of challenging because you have almost no voltage across this transistor. There's hardly any VDS. So it can get very challenging to get very low dropout. So marketing guys, keep it at 300 millivolts. None of this 100 millivolt stuff. By the way, you want to keep the resistance, the series resistance in here very, very low. Because you can see, you start pulling an amp or two out of this output, the drops of the series resistance on chip and in the package, they're going to start adding up and cause you to fail your dropout spec. So it's very, very important, keep the resistance on chip in series with the pass device very low. Output current. LDOs are typically designed to act as power supplies for other circuitry. This means they need to be able to provide a significant amount of output current. Load currents greater than 1 amp are very common. I think Todd just designed a push-pull LDO that's capable of 3 amps, plus and minus. Very nice circuit. 055, I think is the number, if I remember that correctly. I'm forgetting all the numbers now that I've retired, so at least trying to forget. So the LDO must be able to output the max load current and still maintain the regulated output at the correct voltage. And typically that means you're going to have a large pass device here. If you're asking it to spit out 1 amp or 2 amps or 3 amps and regulate, it's going to be a hefty output transistor. Power dissipation. Normally, the majority of power dissipation, and we're talking about heat in an LDO, occurs in the pass device. In this case, the example I show below here, if we assume the output current is 1 amp, and we're dropping 2 volts across the pass device, so the wattage is going to be 1 amp times 2 volts, 2 watts of power. That device is going to get pretty hot. Because this power is not being delivered to the load, it reduces the power efficiency of the LDO. This is just, you're burning this as heat. It's not doing anything for the output. Often LDOs will monitor the temperature of the die, and they'll either shut down or they'll throttle back the output current if the temperature gets too high. This is part of thermal protection. Feedback loop. So the output is regulated using a negative feedback loop. And I kind of show that in the red down below here. The output voltage is sensed using this resistor divider. And then the voltage is fed back to the positive input of the air amp. The air amp compares that to the reference voltage. If the sensed voltage is too high or too low compared to the reference voltage, it will adjust the incoming voltage to the pass device to bring the output back to the regulated value that you want. So in this schematic, feedback here is going into the positive side of the air amp, but you want negative feedback in this loop. The PMOS device here is actually giving you the negative or the inversion in this particular loop. There's lots of ways to do this. I'm just showing one example of how it works. Probably the most common one. Stability. As we said before, anytime you have a feedback loop, you have to worry about stability. The loop must not oscillate under any normal operating conditions. Most LDOs stabilize the loop by placing an external BFC. That stands for big fat capacitor from the output to ground. And we're talking something like 10 microfarads, maybe up to a couple hundred microfarads. So this capacitor typically creates the low frequency dominant pole. And the type of cap can also sometimes affect stability. And this is going to be an external cap. Tantalum caps tend to have higher ESRs. And if you're not familiar what ESR is, that stands for equivalent series resistance of the capacitor. And they're typically in the milliohms up to the low ohm range. Tantalum caps will probably be at the high end. You might get a couple ohms in a tantalum cap. Ceramic caps might be milliohms. Sometimes that ESR can help the LDO. Sometimes it can hurt the LDO. So different caps may add to or subtract from your stability. I just wanted to mention the difference in capacitors might make a difference if you're trying to stabilize the LDO. Overcurrent protection. So many LDOs will protect themselves and the user by setting an overcurrent limit. And this limits how much current the part can source. And if you try to pull more current than that limit, the loop is going to lose regulation. That means it's not going to be able to go to the right voltage anymore. And the current is going to top out near whatever the overcurrent limit has been set at. To do this, you somehow have to sense the output current and then compare it against a known value. Now, I'm not going to show any detailed circuitry how to do this. However, I would like to mention the two most common ways of sensing the output current. So the first one I want to talk about is a pilot device. And this is definitely one of the most common ways we try to sense this output current. The pilot device is connected in a mirror arrangement with the actual pass device. You can kind of see here we have the pilot device hooked up such that it receives the same VGS as the pass device. Typically, the pilot device is going to be way smaller than the pass device. It might be maybe like a 500-to-1 ratio here. So the current in the pilot device is way lower than the output current, but it's a representation of the output current. So this sensed current can then be compared against a reference current And that signal can now be used to throttle back the output current if you determine that the output current has exceeded the overcurrent limit. So the challenge here is you have a very large mirror ratio between the pass device and the pilot device. Also, the VDSs, the drain to source voltage of these transistors, may not match very well. So that can cause inaccuracy. So you have two sources of inaccuracy here, the large mirror ratio and the VDS of the devices. And there are, of course, ways around all this. I'm just trying to give a warning that using pilot devices, you can sometimes get inaccuracies in the current measurement. Another common way to monitor the output is using a sense resistor. And this is pretty straightforward. You just put a resistor in series with the pass device and you measure the voltage across it. Now, if that voltage gets too large, you can use that signal to throttle back the pass device and lower the output current. So the challenge here is this resistor has to be kept very, very low because you can see it's going to add to the dropout voltage. This is in that same path we said, oh, we got to keep all those resistors really low. Well, this has to be a very low resistor. So you're going to be working with a very, very tiny voltage. And that has to be gained up accurately and then compared to a reference. And sometimes gaining up that very tiny voltage can be a little challenging. LDO testing. So just a few words about LDO testing for the test engineer. The resistance of the traces or wires on your test fixture can affect the various measurements. And it's important to take that into account. Dropout needs to be measured directly across the leads of the part. So you want to measure dropout right from V in to V out, right across there. However, V out needs to be measured from wherever the sense pin goes. So you'd really like to measure it right across the resistor stack here. I'm assuming there's a big ground plane on your test board. And all these parasitic resistances in here that are your board resistance, they're going to cause drops and start causing inaccuracies in your measurement. All I can say is provide Kelvin connections on the VN, right on the output pin, and right on the top of the sense resistor. I would put a Kelvin connection right there also. So you can measure all these voltages very accurately, and you don't have to worry about taking into account drops, the voltage drops in your test fixture. Okay, so that's it for LDOs. I'm going to give a little summary here. LDOs are a type of DC to DC step-down regulator. They can only step down voltages. They're pretty low noise because there's no switching noise. It's all DC. There's no inductors in here. Typically pretty good power supply rejection. One of the nice advantages is they can be embedded inside a chip to generate various on-chip voltages, and they're pretty ideal for a wide range of applications. The disadvantage is they're pretty crappy for power efficiency, and they can dissipate a lot of heat. You got to take the good with the bad. That's LDOs. Okay, we're going to move on to buck converters. Similar to an LDO, a buck converter is another type of DC to DC step-down converter. We're always making the input voltage lower. Its job is to take a DC input voltage and produce a lower, useful DC output voltage. However, that's where the similarity to an LDO ends. Buck converters use a completely different method to generate their output voltage called pulse width modulation, or PWM for short. The idea is to control the opening and closing of a switch connecting V in to V out with just the right duty cycle, frequency, feedback, and external components to generate the desired output voltage. So that sounds pretty complicated because there's a lot going on. And I'm going to try to keep it simple while attempting to explain how they work. However, I'm definitely not a buck expert. So for Moni and James, you guys can feel free to correct me, be nice about it. But I'm going to give it a shot. Like I said, I'm definitely not a buck expert, and this is an introduction class. So it's not going to get too complicated, hopefully. Okay, so let's look at a very simple example first. What if we have a 6-volt supply, but we really want to produce a 3-volt output? And we want to do it using an on-off switch. One way to attempt this is shown here. And what it would look like is if we would just open and close the switch with a 50% duty cycle. So what we would get, we'd get 6-volt half the time and 0-volt half the time. And if you look at that, what that does, it gives you a 3-volt average, time average. So we were able to take our 6-volt and convert it to a 3-volt signal just by opening and closing a switch. However, it's time average. We really want DC. Something like this might work if you're controlling the speed of a fan in a computer or maybe dimming a light bulb. But what we want is really DC. We need to find some way to smooth out these pulses. Half the time, there's no current going to the load when the switch is open. And to fix this, we need to add an inductor in series with the load. Inductors are similar to that coil of wire I showed earlier. When you run a current through an inductor, it creates a magnetic field. And the size of that magnetic field grows and shrinks with the amount of current, storing energy or releasing energy as it does. So the magnetic field acts to resist instantaneous changes in the current by either growing or collapsing. We can use this property to help keep current flowing to the load even when the switch is open. So let's go ahead and add an inductor. However, we immediately run into a problem. The magnetic field of the inductor builds up while the switch is on. However, when we open the switch, the magnetic field starts to collapse, but there's no path for the inductor current to flow on. Therefore, we need to add a diode to give the induced current a path to flow on while the switch is off. I believe this is referred to as the freewheeling current. When the switch is closed, the current from Vn flows through the inductor and the load, and it causes the magnetic field in the inductor to expand. When the switch opens up, the magnetic field of the inductor starts to collapse, inducing current to flow on this path I show in the red here, and the current returns to the inductor through this forward bias diode. So by adding the inductor and the diode, we provide a way to deliver current to the load, no matter what state the switch is in. However, Vout will still bounce around a lot, and we want DC. So to fix this issue, we need to add an output capacitor. That's what I'm showing here. In addition, we need to open and close the switch very fast because we never want the magnetic field of the inductor to max out or collapse all the way to 0. We just want it to vary, but never all the way max or all the way min. And we also never want the cap to reach full charge or 0 charge. So this is known as continuous conduction mode, or CCM for short. Now for speed reasons, we're going to go ahead and replace that switch with a transistor. And there you have it, a buck converter in its simplest form. Vout can be set by picking the duty cycle of the switch, in this case a transistor, as long as the inductor and cap are kept in continuous conduction mode. So if you have a 6-volt input and you want a 3-volt output, you just turn the transistor on and off with a 50% duty cycle. If you want a 2-volt output, you use a 1/3 or a 33% duty cycle. This is known as pulse width modulation, or PWM. So by changing the width of the pulses, controlling the transistor, you can set Vout. So why do we go to all this trouble just to generate this output voltage when an LDO could do it for you, no problem? The answer is power efficiency. Power efficiency, like we said, is basically a measure of how much of the input power is delivered to the load. And you'd like that to be close to 100%. Think back to that transformer example we talked about earlier. For AC power transfer, the transformer was typically like 97, 99% efficiency. We really want something like that for DC power transfer too, and LDOs just don't cut it. LDOs are great for low noise applications where you don't mind burning some power in the pass device as heat. However, if you're really concerned about power efficiency, bucks are the way to go. So let's go ahead and examine this a little further. So let's look at the power dissipation of each element in the schematic. Well, ideal capacitors and ideal inductors, they don't dissipate power. They just store energy and release energy in either their electric field or their magnetic field. Now, in reality, capacitors and inductors both have some series resistance, so they're going to dissipate a little power, but not much. Their transistor has two states, since we're using it as a switch, on and off. During the on state, the voltage across the transistor is low, and power is voltage times current. So if the voltage is next to nothing, that means the power is next to nothing. During the off state, again, it's a switch, the current is low, and power is voltage times current. There's no current, there's no power. So we're hardly dissipating any power in the switch. Turns out the diode ends up dissipating the most power in this example. So the diode is probably forward biased around 0.7 volts, maybe a little more at high current, but it only conducts current for half the cycle. It's only during the freewheeling part of the cycle. But that's a significant piece of power compared to everything else that's almost no power. So this arrangement with the diode is known as a non-synchronous or asynchronous block. And one way to improve its power efficiency is to replace the diode with another on-off transistor that is going to dissipate much less power than the diode. Now, this adds some complexity. So here we have the non-synchronous buck with its diode. We've taken out the diode and we've put a transistor in here. And that transistor can operate at much lower voltages than the 0.7 volts of the diode. The only problem now is we need to synchronize the switching between these two transistors. They need to ping pong back and forth. So this is known as a synchronous buck. So earlier we saw that LDOs use a feedback loop to keep the output at the desired voltage. And the same is true for buck converters. However, buck feedback loops are a little more complicated because it regulates the output voltage by adjusting the pulse width modulation duty cycle. So let's look at each component in this feedback loop. So everything starts with this resistor divider over here. Very similar to the resistor divider we saw in the LDO case. So the resistors are picked such that the sample voltage right in the middle will equal Vref when the output is at the desired output voltage. The sense voltage is then fed into a compensator and an error amp. The compensator is a filter to help the transfer function of the loop. And I'm not going to talk about any complexity here, just hand wave. It's just helping the transfer function. The other input of the error amp is connected to a reference voltage, very similar to the reference voltage we saw in an LDO. And this would probably be generated by an on-chip band gap, or it could be brought in from the outside world. The output of the error amp is a DC level that represents the error or difference in the sensed voltage from the reference voltage. You're trying to get the sensed voltage to go to the reference voltage, but if there's an error, the output of the error amp is going to move up and down depending on whether that error is positive or negative. So the DC output of the error amp feeds into a comparator, and the other input of the comparator is driven using a sawtooth waveform. This is probably generated using a constant current into a cap. I think I showed an oscillator a few months ago that produced a waveform similar to that. That DC level is compared to the sawtooth waveform to create a pulse width modulated signal, PWM, that drives the main transistor. And the PWM is going to be basically a square wave. It's the output of the comparator. However, the duty cycle is adjusted by this feedback loop such that the V sense voltage is driven to the reference voltage. Let's see how that works in a little more detail. So the output of the error amp is shown here in red. and it's going to move up and down with the error. And it's compared to this green sawtooth waveform. The arrow riding up and down on the sawtooth alters the duty cycle of the comparator, shown in blue. And I show three different examples over here. One is, let's say the error was right in the middle of the sawtooth waveform, and that might be when V sense is right where you want it equals V ref. We might be getting a perfect 50% duty cycle there. If the error tends to go up, you can see the comparator output now is going to change the duty cycle of the PWM signal. It's going to reduce the duty cycle. Similar, if the error goes down, it makes the duty cycle longer. That gets fed around through this feedback loop and will bring the V sense very close to the V ref voltage. Now, this is all kind of tricky. You have to have a lot of negative feedback and compensation in this loop to make this happen. But I'm just trying to give you an idea how these PWM feedback loops work. So this scheme works pretty well for load regulation, meaning how fast does the loop respond to an output load? And you can kind of see if you change the output load, V out is going to get sensed by the error amp very quickly and make adjustments for it. However, what about line regulation? What that means, how fast does the loop respond to changes in V in? And at first glance, this is not going to be very good, because if you changed V in, that signal would have to come in here, go through this massive low pass filter before it could get sensed by the error amp and corrected. I think this is called voltage mode feedback, and it's probably pretty good for output regulation, but not very good for line regulation. To speed up this response, there is another architecture that alters the magnitude of the sawtooth waveform based on Vn. So as you change Vn, you can alter the magnitude of the sawtooth waveform, and that can affect the pulse width modulated signal almost instantaneously. I think that's called voltage mode feed forward. This is a pretty common technique used to improve the line regulation, and you already have pretty good load regulation. Now there's yet a third one that I'm really not going to talk about here, where you measure the peak current through the inductor, and I'll briefly talk about that when we get to boost converters. Okay, so high side, low side switching. So now let's backtrack and let's replace that freewheeling diode with a transistor for better power efficiency. And then we're going to redraw the schematic. Now we've added a new block called the PWM controller. And the purpose of this block is to synchronize the switching of these two transistors. And the PMOS device on top here, we're calling the high side driver, and the NMOS device on bottom here, calling the low side driver. These two transistors, they turn on and off out of phase with each other. During switching, there's going to be a slight overlap in time where both transistors are off, and this is known as dead time. We want to avoid both transistors on at the same time, because that could cause shoot-through current. If these both came on at the same time, you could have shoot-through current from V in straight to ground, and that would not be good. You might blow something out, or at least your power efficiency wouldn't be very good. So I basically wanted to introduce the term high side and low side. Let's compare the current flow during high side and low side switching. During high side switching, the current flows from V in through the inductor and the load, returning to ground, just like it did before. During this cycle, the inductor stores up energy in its magnetic field. You're charging the magnetic field. During low side, the magnetic field in the inductor starts to collapse, returns some of that stored energy, and it keeps the current flowing, but it flows now on this loop on the right here. This is similar to before, only instead of flowing through the diode, now we have the low side switch. So we have to turn the low side switch on during that part of the cycle. So in continuous conduction mode, using a low side FET instead of a diode gives the best, lowest power dissipation. However, sometimes bucks can enter what's called discontinuous conduction mode. This is where the inductor current drops to zero. And this typically happens when the output current demand is very low. So you're not pulling a lot of current out of the part. During low side, you can actually get current going backwards through the low side FET with the cap going in reverse through the inductor and the low side FET to ground. And this can cause some losses. If your controller is smart enough, it can sense this. And this is called diode emulation. And what it can do is it can just shut that low side FET off. And a lot of times you'll put a diode in here, maybe they use the body diode that's already in there. The buck guys can tell me whether there's an extra diode or you actually use the body diode. If you're in diode emulation mode, you're pretty much shutting off the low side FET, and now you're back to the same freewheeling diode you had before. However, at low output currents, the power losses in the diode might be less than the losses due to reverse conduction through the FET. So when you hear about designers talk about diode emulation mode or a synchronous buck with diode emulation mode, this is what they're talking about. Okay, PMOS versus NMOS. We'll get to Seiju's question here. So you may have noticed I've been using a PMOS transistor for the high side and an NMOS transistor for the low side. These both make sense because they're the easiest ones to drive. The source of the high side PMOS transistor is tied to Vin. So it's very easy to generate the VGS needed to turn it on. And no problem generating that VGS. Likewise, the source of the low side NMOS is grounded. So it's real easy to turn it on. However, NMOS devices are faster, and they're about 3x more area efficient than PMOS devices. That means it's desirable to replace this PMOS device on the high side with an NMOS device. However, that starts presenting some challenges. The main challenge with an NMOS high side is getting enough VGS to turn it on. And a common way to do this is called bootstrapping. And I'm sorry, the schematics are starting to get a little complicated here. I'm trying to keep it simple, but so in this schematic, the high side PMOS device has been replaced with an NMOS device. There's the NMOS device on the high side. And as before, the low side FET is an NMOS device, and it's driven with the standard voltage it had before, ground and Vin. However, those voltage levels aren't going to work for driving the high side FET now. The high side transistor is driven with a level shifted or charge pump voltage to give it enough VGS to act as a low resistance switch, which is what you need. Now, notice we've added this bootstrap cap and this boot diode. So when the low side FET turns on, it grounds the bottom plate of the bootstrap cap. This charges the bootstrap cap because the top plate of the bootstrap cap is tied to Vin through this diode. So you're going to pull the bottom plate down, top plate's sitting up at a diode below Vin. So we've charged up this bootstrap cap. When it comes time for the high side to conduct, the stored voltage on this bootstrap is used to provide VGS for the high side NMOS. As the output voltage rises from ground to Vin, the voltage on top plate of the bootstrap cap, that's going to rise with it. Now notice how the high side buffer gets its power from the cap, and it's referenced to the source, not ground, of the high side device. The boot diode will be on chip. However, the bootstrap cap is often external. So, sorry, this is a little confusing. Just be aware when people talk about all this bootstrap capping and diode, it's so that we can use an NMOS device as a high side device. It's a way of giving us the VGS needed to make that device work. Okay, buck converter summary. They're a type of step-down power converters. They often have power efficiencies well over 90%. And hand in hand with that, you have low heat dissipation. You have a wide input and output voltage range. And bucks are ideal for many power applications, especially portable devices. If you're running off a battery, you don't want to dissipate much power. The disadvantages are switching noise. This thing ping pongs all over the place. And you need an inductor. So a boost converter is another type of switch mode power supply. However, instead of stepping down the input voltage like a buck does, it uses very similar principles to step up the voltage. Let's take a look at a typical schematic. What we've done here is we've taken all the same components of a buck and just rearranged them. Now, when the switch closes, as shown down below here, current from Vin flows through the inductor and returns right through the switch. It flows in this path right here. So this expands the magnetic field of the inductor. Now, when the switch opens, what happens is the current will flow on this other path, and the magnetic field of the inductor starts to collapse. As the magnetic field collapses, the voltage across the inductor starts to increase. And that voltage is added to the Vin voltage, and that shows up on the output voltage. This is output voltage cap through this inductor, through this diode. So that reverse bias diode prevents this cap from discharging during the on cycle when the switch is on. So it's kind of like it's kind of like a charge pump, but you're, instead of using a capacitor to pump up the output, we're using the magnetic field of an inductor. So just like in a buck, the switch, inductor, and capacitor, they don't dissipate much power. Most of the input power is dissipated in the diode. And just like in a buck, we can replace that diode with a transistor to reduce its power dissipation. So here I've gone ahead and replaced it with a transistor. So in this schematic, I've replaced the diode with a PMOS transistor, and I've drawn in the body diodes just to give you a better idea how everything is connected. So this would be called a synchronous buck, because now you have to synchronize the switching of these two transistors. They're always going to be out of phase with each other, just like in a buck. And though, just like in a buck, there's going to be a short time period where they're going to be both off. That's known as the dead time. You never want these both to come on at the same time, because that would give your output cap a path to discharge to ground and potentially cause shoot-through current that you'd like to avoid. So the output voltage is controlled by the duty cycle of the switching and regulated by a feedback loop, just like in a buck. So in continuous conduction mode, that means the current in the inductor never drops to zero. The equation for a boost converter is shown in red here. It's basically VL equals Vin divided by 1 minus the duty cycle. So this is sort of the ideal boost equation. So if the duty cycle is 50%, the output is going to be twice Vin. The duty cycle is 75%, the V out is going to be 4 times V in. So the feedback in a boost converter is similar to a buck, only current mode feedback is used instead of voltage mode feedback. And again, I'm not an expert on this, but what I've read is that this configuration tends to give you a right half plane zero. Anybody that knows about transfer functions knows that right half plane zeros are bad news. And that means you're probably going to oscillate. Supposedly, by using this current mode feedback, companies have been able to address that. And what they do is they sense the current coming out of the inductor, and instead of that sawtooth ramp that we fed into the comparator the last time, now we're feeding a ramp that's kind of a representation of the current through the inductor. And then that is used through an RF flip-flop with the set periodically being pulsed with a clock. I don't want to get into this in any great detail, but what I'm really trying to tell you is you're almost locked into using this current mode feedback if you're going to be doing a boost converter. Voltage mode or voltage feed forward mode isn't going to work. You're going to have to do this current mode. But this is a topic for a more advanced talk. We'll get Moni or James down here, one of the Buck guys, to talk about this. Anyway, so that's all I have on boost converters. And basically, to summarize, but it's a step-up converter. Has high power efficiencies, low heat dissipation, wide input-output voltage range, and it's ideal for many low voltage applications. Solar panels I thought were interesting. A lot of times you get these photovoltaic cells, and you want to boost them up to a higher voltage you can do something with. I could see that being useful on a spacecraft, especially. So might want to think about that. I know we probably do make a couple of boost converters right now. I think the old HS 1825 and again, the disadvantages are, these things are ping-ponging all over the place, so you have switching noise and you need an inductor. Okay, do you want to hear the bonus topic?
Yes.
All right, it's not much of a bonus topic. Nothing very interesting. I'm going to talk about metal slotting. So most materials expand or contract at temperature, like mercury inside a thermometer. A measure of this property is known as the coefficient of expansion. And ICs are constructed using a wide variety of materials. And all these different materials have different coefficients of expansion. The aluminum we use for our metal lines has a coefficient of expansion that's like 100 times greater than the silicon dioxide that surrounds it. As the temperature changes, the aluminum expands and contracts much faster than the surrounding oxide, and that creates a lot of mechanical stress. If that stress gets too great, it can crack the oxide. So expansion and contraction, they occur in all directions, up, down, left, right. However, in general, the widths of our metal lines are much greater than the thickness. The thickness might be a micron, but we can have metal lines that are 10, 20, 30, 100 microns wide. So the wide metal lines will expand and contract more than the thin metal lines, causing more mechanical stress. Fabs have rules to tell us when we need to address this issue by adding stress release slots to the wide metal lines. And so for thin metal lines, it's no problem here whatsoever. But for the wide metal lines, you're going to have to add some slotting in here. And the fab gives us guidelines on how to do that. Now, for example, Taiwan Semiconductor says any metal line wider than 35 microns needs to have slots, and it tells you how big the slots have to be and how long they have to be. It does fortunately make exceptions for bond pads, which is nice. So the purpose of these slots is similar to the stress relief grooves you'll see in a concrete sidewalk. They allow for the expansion and contraction while preventing cracking. When we run DRC rules, it's going to flag any area where you need to add slots. So, by the way, make sure to run the slots parallel to the current flow, not perpendicular. You can just see that, this example is very easy to see, but sometimes it's not so easy to see because you'll be looking at and say, which direction is that current flowing on? But you don't want to interrupt the current flow. You want the slots to run parallel to the current flow for electromigration reasons. Okay, conclude the talk. DC to DC converters are part of a larger family of products called PMICs, stands for Power Management ICs. Basic job is to convert an input voltage to a desired output voltage that can then be used as a power source for other circuitries. I hope my talk has added to your knowledge of the various types of DC to DC converters and how they work. If anything I discussed today that's still a little confusing, ask Moni. Sorry. I've attached a glossary of terms at the end of this PowerPoint that you can look through and read up on.